Okay, great. Yeah, so Jon Wyrick from NIST, he's going to tell us about solid-state atom-based devices.
Yeah, thanks for the introduction. So I think a lot of you are probably more familiar with some of the other platforms that are used for quantum simulation, things like trapped ions and cold atoms and maybe also gate-defined quantum dots and things like that. This is single atoms that we've positioned in silicon, single donor atoms in silicon. And at least talking with some of you yesterday during the reception, some of you weren't really familiar with this system as a method for quantum simulation. And I think what that means is I can just make up whatever I want, and I should be able to fool at least some of you, hopefully, about this. And maybe before I really jump into everything, I want to say that this is actually an effort of quite a group of people where, for example, we've got, from NIST, we've got an atom-based fabrication and measurement sort of subgroup, and there's three of us permanent staff members, Rick and myself, and we each sort of lead different parts of how we do fabrication and measurement. And we also work very closely with Garnett Bryant, who's a theorist, and many of you know him. And actually some of the work in this talk is also, we've been working with Ihsan Khatami as well, from San Jose State University. And what I would say is that all of these people are leading important aspects of this work, and without any one person, we wouldn't be able to do this stuff. So I don't want to give the feeling that it's all me doing this. I want to really emphasize everybody that's working this. This is the outline of my talk. I'll start with sort of introducing this system and explaining how we can use it to make Hamiltonians that we want to run simulations on. And then I want to talk about how we actually fabricate these devices. It's a pretty interesting technique, pretty amazing in my opinion. And then I will talk about some actual experiments that we've been doing. We're still, I think, in the very early days of using this system for quantum simulation, but how we've been working towards understanding whether and how it maps to a Hubbard model. And then I'll finish up with sort of saying where we're at and what things we're working on to move this forward and make it a more developed platform for quantum simulation. So to start with, we can think about silicon crystal. If you think about the bulk of silicon, we like to think of it as a vacuum, where what we mean is we've got electronic states in, say, the valence band that are all filled up, and you've got empty states up in the conduction band, but then there's all this empty space, at least in energy space, where that's our kind of vacuum in this system. And we can imagine putting phosphorus atoms as dopants on a silicon surface like this, where we really try to put them exactly where we want them. And if we now slap some more silicon on top so that those phosphorus atoms are surrounded by bulk silicon, then we have these potential wells that have been spaced out according to whatever it was that we wanted. And of course, they introduce discrete states into that silicon vacuum. So this is our system that we're working with, where we can build Hamiltonians just by adjusting the positions of these phosphorus atoms and other details about how they're put into the lattice. And to go a little bit further, we can also introduce additional control structures. So we can have electrodes, for example, this is supposed to be a source and a drain, or we can have electrostatic gates, which are not tunnel coupled to our atomic system, but are a little bit further away. And so you can imagine, say, putting a little bit of a bias on this gate, and essentially what happens is we will tilt will tilt the states along this direction. And so then we can start filling some of these electronic states that were available. They come below the Fermi energy, we fill them up so we can kind of control how we're filling things into this system. We can also imagine fabricating top gates, so that's what I'm showing here, that maybe have more of a global effect on the system. So I guess you can see we can sort of shift things up and down like that. We can also fabricate antennae, whatever the plural of that is, where maybe we can start if we also impose a background magnetic field and Zeeman split the states. Now we can also imagine having a two-level system where we can even perhaps coherently manipulate the electrons from spin up to spin down, or even the nuclear spins. We work with phosphorus atoms, and so they have a nuclear spin that can also potentially get manipulated. So I'll say that most of this talk I'm really focusing on what I would call analog quantum simulation, but I know a lot of people are thinking maybe also in terms of digital quantum simulation, working with qubits. So this is also a system where we can make qubits. Or we may find that we just want to run our simulation. We want to be able to have coherent control over the spin. So that's something that we can do. So now I'll kind of tell you about how we actually build these devices. And the first thing is the key enabling technology that we use to make the devices is a scanning tunneling microscope. It's a atomically sharp metal tip that is brought into a few angstroms of a sample, and we can tunnel electrons either from the tip to the sample or the other way by biasing the tip. This is a famous experimental tool that was back in the 90s. It was used to move atoms around on metal surfaces, and for instance, what you can do is corral the electrons of a surface state into these really interesting standing wave patterns. So you're already seeing a kind of quantum device here. One of the limitations of this kind of system, though, is that this is done at like 4 Kelvin, and it's done in an ultra-high vacuum system. So it only really lives for some, for maybe a few days or something in this environment. You can't, say, take it out of vacuum. You can't warm it up and, say, integrate it into some larger system. What is really interesting about the technique that we do is that we can actually build quantum structures that we can take out of vacuum. And since we're doing them in silicon, you can imagine that they may be able to get incorporated with other structures using standard silicon processing techniques. So the way we do this is we start with a silicon crystal where we've managed to terminate the surface with hydrogen atoms. That's what the white atoms are here. And then we bring the STM tip into contact or tunneling contact with that surface. And these are the kinds of images we can get out of the STM when we're doing that, where what we're able to do is we can bias the tip enough that it actually blows the hydrogen atoms off the surface. They're weakly bound enough that if you provide enough bias, they just come off and float into the vacuum. And the bright areas in this image are regions where we've removed hydrogen atoms, whereas the darker areas are where hydrogen atoms still remain. And what we can do next is we can leak in phosphine gas, which is phosphine is a phosphorus atom with 3 hydrogen atoms. It's a highly toxic gas, so just be careful if you try to do this at home later. We've got a lot of safety measures in place so that we're not particularly worried about it. But what's interesting is that what we really did when we used the STM tip to remove hydrogen atoms from the surface is we created a template that these molecules will only stick to the sites where we've removed hydrogen atoms. And otherwise they just sort of bounce off the surface. And the chemistry that's going on when we do this is here you can see an example where I've got two hydrogen atoms removed. When the phosphine molecule comes down, in order to actually stick to the surface reliably, one of the hydrogen atoms has to come off and sit at a nearby empty site, which is what's going on here. So you may have noticed in this image there are some random looking bright spots, which are places where there were hydrogen atoms missing in our initial resist. That's not really a problem for us. The phosphine molecules won't stick there because they need that extra site to remove at least one of their hydrogen atoms. We can then heat this up, and ideally what happens at least is that the hydrogen atoms go away from the phosphine molecule and it embeds itself into the surface, and so we can say that it's incorporated into the lattice. And if you've done that, then the next thing that you can do is you can overgrow silicon on top of that. And we're even able to now take this thing out of the ultra-high vacuum environment. We can put it in an ambient AFM and do what are called Kelvin probe measurements, where we can actually see the electronic signature of a device that has been buried below the surface. You can't see the really interesting, say, array of dopants or whatever it is that we've made here, but what you can see are all of the leads for the electronic control structures that we've built to be able to do measurements on this system with. And those show up really nicely, which means that we can work out where that buried device is located with a pretty high degree of precision. And we can come back and deposit palladium on the surface to make contacts to this buried device. You heat up the palladium and it makes what's called palladium silicide. It sort of works its way down below the surface and meets that buried device at the different places that we wanted to make contact to. And so here's kind of a picture, an optical microscope image of one of these completed chips where you can see that those palladium silicide contacts then come all the way out to wire bonding pads. So we can wire this thing up and say put it in a dilution refrigerator or whatever kind of measuring equipment we want and run this device. So that's how we make these things, and now I'll tell you about the experiments that we've done recently where we're evaluating how well we can use this to do Hubbard model simulations. So the basic idea is that in this system, we've got the dopant atoms. When we talk about the tunnel coupling in the Hubbard model, it's about how the electrons are coupled from one atom to another. So if we want to change the tunnel coupling, the simplest thing to do is just make the atoms be closer when we build one of these devices. There's the on-site repulsion term is just as simple as, well, if you put two electrons on one atom, they've got Coulomb repulsion, right? And so if we think about a phase space diagram, we're over here on the repulsive side. If we wanted to look at things on the retractive and the attractive regime, we have to be, I think, pretty creative in how we make devices, and I don't know exactly how we would do that. We also have another knob that we can turn because we're able to put in these top gates and side gates and everything. We can shift the chemical potential up and down and adjust the occupation of these different sites. So that's another knob that we can turn, which means, of course, there's another direction we can go in phase space. So we've got sort of this three-dimensional diagram that we can imagine moving around on with our Hubbard model. When we're modeling this, we also include the nearest neighbor repulsions as well, so that's what I'm showing here. And one other thing I'll say is that the experiments that we've done so far are on what I would call imperfect or disordered systems. You might remember from those STM images before that the sites where we wanted our atoms to go were kind of blobby looking. And what that means is that we don't necessarily have, in these experiments, we don't necessarily have exact control over how many dopants go into each site. And so that means that we also have to think about the fact that the on-site Coulomb repulsion could be different depending on how many atoms are at a site. And actually with those side gates and everything, then the chemical potential at each site could be shifted up or down. So that's also accounted for here. So what we've done is we've made a series of 3x3 arrays. Here are the SDM images of those, where what we did, again, the simplest way to control tunnel coupling between these systems is just to fabricate multiple devices and make the lattice constant smaller each time. And then we've got the kinds of measurements that we're doing right now is we run a current between source and drain, and with a small bias between these two, the electrons will hop onto the array and tunnel through it and hop off. And we can measure the current as we vary the two side gates that we've got here. And so the reason we picked 3x3 is that this is actually a system that you don't really need a quantum simulator to model. You can also model it just straight up with a classical computer. And so we're in sort of the stage where we're evaluating how well can we map to and from the Hubbard Hamiltonian for this system. And so we've done a fair amount of calculations just on classical computers to try to compare these two setups. So if we look at the case where we've got the different sites are more or less decoupled from one another, then we get an image that looks something like this, and I'll quickly walk through what we're actually looking at. This is what we would call a gate map. If we go down to the bottom left corner here in gate space, then we've got negative bias being applied to both gates, but in terms of what the electron sees, it sees sort of a positive potential there, right? It's repelled by the gates. So we see something that looks like this in terms of a potential landscape created by these two gates. If we go to the bottom right corner, then we've got something more like this, where now we've got a positive voltage on one gate, which is attractive towards electrons, and then we've got repulsion on the other side, so we're able to tilt our potential landscape across the array. The top right corner is sort of the opposite case from the lower left corner, which means now we've got more of an attractive region for electrons in this array. And so you can think as we go diagonally up the array, that's how we're able to fill more and more electrons into the system. And then the top left corner is just sort of the mirror image of what we've got in the bottom right corner. So, as I said, we can also model this system. It's small enough that we can imagine modeling it. And that's what this is a picture of, where we're now modeling what the occupation should be at each of the gate values. And you can see that qualitatively it seems to match pretty well. Quantitatively, maybe not so much. And we attribute that to the fact that, again, we're working with some amount of disorder in our system. So just to walk through how this electron occupation works in a little bit more detail, you can imagine starting here in gate space, so we've just zoomed in on some region, and so here's sort of the configuration of our two gates. These white boxes are how many electrons are on each site based on our best understanding of how many atoms are at each site, and therefore how many electrons we think are sitting on those. And if we shift gate 1 lower in potential space, higher in voltage, then we're going to the right here. And as we cross this region, we add one more electron. And so I should say, in the experimental map, we've got mostly regions where there is no current flowing, and then the place where we see current flowing, that's because we're adding extra electrons to the array. We're able to hop on and hop off of the array. So this is showing the boundaries between each of those regions of electron occupation. So, not surprisingly, the place where the gate has been made more attractive to electrons, we get more electrons there. We can similarly increase the voltage on the other gate, and we see extra electrons coming onto the other side. So this is just to give you a sense that we're able to control the occupation on the array, and that it, again, at least qualitatively matches what we would expect from a Hubbard model simulation. So there's our little region that we made. And so, as I said, we made 3 of these systems where we vary the lattice spacing. And what we see is that in the top gate map, we see behavior that is most indicative of more or less decoupled electrons. And as we go down in this image and get to higher tunnel couplings, we start to see behavior that looks almost like these are making a single dot. So this is, in a sense, like a metallic system. Yes, oh, running out of time? 5 minutes, okay, sounds good. And then we have an intermediate case here, where actually, if we've got more electrons filled into the system, it looks more metallic. If we have fewer electrons filled into the system, then they still look decoupled down here on the bottom left. And essentially what that means is that we're moving in our phase diagram from starting out at something that looks like at least a discrete sort of, or a finite analog to a Mott insulator. And as we go down this way, we're shifting to the left into a metallic regime. So we can also start to think about how we're filling spins into the array, which is what this picture is supposed to show. So now the red or pink regions are spin up and the blue regions are spin down. And what our theory tells us is that we would expect in highly tunnel coupled regimes that we have an antiferromagnetic state where we're getting sort of as many spin up and spin downs all, as we're filling in one by one to minimize the total spin of the system. And so that's kind of shown here where if we're starting out with, say, a total spin up of 2 and a total spin down of 2, if we add another electron to the system, then we go from 2 to 3, and you can sort of see where those electrons are, where those spin ups are coming into the system, so that the 3 and the 4 are almost canceling each other out. If of course we expect if we go to lower tunnel coupling, then we should have more of a Hund's rule type scenario where maybe we're filling all spin down first, and then only after having filled all spin down, we start to go to spin up. We have also started to do experimental measurements on spin filling into these arrays. This is actually work from the Zurek group in Australia, where they're increasing, they're moving a gate up, and this is on a gate-defined quantum dot. They're shifting a gate voltage where they can fill electrons into the quantum dot one at a time, and by then also varying magnetic field, you can extract from the slope of this whether it was a spin up or a spin down electron that was getting filled in. And there's an interesting, and so, if you think about this in a very simple way where you've got, say, spin down and getting filled first and then spin up, because of Coulomb repulsion, of course, you have an addition energy that you have to overcome before you can fill in that next spin. But you can see this kind of positive slope here that is indicative of a spin up. And then at some point, there's a kink and it switches to a spin down. And that's very simply understood as, you have a system that actually has multiple levels, right? And as you increase the magnetic field, then the energy for spin up keeps shifting upwards until at some point there's a crossover and it becomes more favorable to fill in a spin down electron on that next highest level. So that's what you really think is going on when you hit one of these kinks. And we're able to do a similar kind of measurement on our system where we see the same sort of thing happening. We can see whether we're filling in spin up or spin down. This is the metallic system where we would expect to see kind of an antiferromagnetic behavior. We're not actually seeing that, and so this is one of the things that we're very curious about, what it is that we're seeing. We also see these slopes that seem to be indicative of filling in more than one spin at a time or something. We suspect that, and I should mention that the reason this is kind of up and down is that we're ramping magnetic field to 7 Tesla, then back down to 0, and then to -7, so that we can just see that our results are reproducible and make some kind of symmetric sense as for as you go from positive to negative magnetic field. So we think that maybe our lack of understanding about what's going on in this system is probably related to the disorder in these arrays, and I think that's maybe a good reason to say, to motivate what we'd like to do moving forward, which is to make perfect arrays. So, and this is something that I could talk to you guys for like hours on, because this is part of what I'm leading. So I think I've got another hour, is that right? I'm basically out of time actually. But so what we're able to do is actually, we can add an extra step in the process where we can come back with the STM tip and manipulate species that have been deposited so that we can strip hydrogen atoms off of it. And we've done simulations of what the STM images should look like at every step along the way so that we know exactly what we're doing to these things as we peel hydrogen atoms off. And then when we heat up the sample, we really get single phosphorus atoms going in where we want them to go. So we're able to start making systems now where they're perfect. The other alternative to this would be to actually, rather than making small phosphorus donor clusters, you can make larger structures where you have lots of phosphorus atoms, and so then the sort of the signal to noise ratio goes down that way. And I think Sam Gorman, who's going to talk later in the week, I think he's going to discuss doing it that way. He's from the Michelle Simmons group in Australia. So there are a couple of ways you could do it. I'm particular to this way because this is kind of my mandate, like make perfect systems, and it is something that we think we could do. In fact, here's an example of a 2x2 array that I've made with single phosphorus atoms at each site. And so another thing that we want to do is improve how we're doing measurement. So we're working on bringing up, we can build extra structures into the system where here we've got a single electron box that can be used for charge sensing on the array. And we want to bring in RF reflectometry signals so that maybe we don't have to rely so much on transport measurements through the array. The other thing you can see here is we've got a lot more gates where now maybe we can start imagining independently controlling each of the dots on an array. We're also working on being able to have top gates in the system where maybe we can even have aligned top gates to add some independent control that way. And of course, as I showed earlier, we'd also like to be able to have an antenna where we can do coherent manipulation on the electrons around these single phosphorus atoms. And so we've got a lot of test structures where we build a single electron transistor. That's what this part of the picture is here. And then we put it next to a single phosphorus atom. And then we can like move electrons onto or off of that single phosphorus atom one at a time, and hopefully then be able to do coherent manipulations of that. So that's what we're working on to start bringing this system up to the next level of quantum simulation, and also as both an analog quantum simulation architecture and also a qubit architecture as well. So maybe I'll just skip the summary, but you can just imagine everything that I said. I will quickly advertise, I think tomorrow we've got two theorists from our group who are going to be talking about Nagaoka ferromagnetism in bi-N arrays, which again also sort of require atomic perfection, and also how do we really map? How do we map accurately, say using atomistic models to get to and from the Fermi-Hubbard model? So with that, I'll take any questions if there's time left.
We have time for a question. Oh. Okay. Really beautiful slides, by the way. Love the 3D images and very cool results. Can you tell us a little more about the susceptibility of these structures to intrinsic charge noise in the devices and the sort of what that means for T2 type of coherences in the system. I'll look there.
Yeah, so, I mean, you know, when you look at one of these pictures, you can see like various defects in the silicon lattice and things, and so there's always a risk of getting charge noise from those if those are charging defects. And also if we're adding top gates, if we've got like an oxide and things on top like that, that can potentially add additional charge noise. So I would say at this point we don't necessarily know exactly how good we can make it. But certainly there's work from groups that say implant ions or implant phosphorus atoms into silicon, where usually they see actually pretty good long lifetimes for the spins. I don't remember what those numbers are actually off the top of my head. So particularly if you say use isotopically enriched silicon. So, you know, I'd say we're early enough in the game that we're not as worried about that yet. But it's something that we're also maybe in a good position to probe because of the fact that we can really put single atoms where we want. And with the SDM, we can see what many of the defects nearby are and maybe characterize what they are. But yeah, I'd say we're still kind of early in the game of figuring all that out.
Yeah, great. So let's thank Jon again.